Welcome. The following presentation has been produced in relation to the development of a wastewater treatment plant at Athlone Institute of Technology for the treatment of wastewater produced by the campus's engineering building. TNLS have been appointed consultant engineers and project managers for the project. The TNLS project team consists of Trevor Smullen, project manager, Liam Mahan, Niall McHale, and Stephen Parker. The project consists of the design, installation and commissioning of a wastewater treatment plant for AIT. The plant is required to be designed for the treatment of influent from 400 persons currently and is envisaged for growth over the next 3 to 5 years up to 500 persons. Discharge requirements from the treatment plant are required to be 25 mg per litre BOD and 35 mg per litre suspended solids. Treated effluent is then required to be discharged to municipal sewer at the eastern entrance of the institute. The following presentation will last approximately 20 minutes. The first section will deal with the project management planning for the project. The second section will firstly deal with the system and structural design of the SPR unit and then the hydraulic design of the sewer system. The third section of the presentation will deal with the construction phase of the project. The fourth section will deal with a WordPress website which was utilised during this project. And at the end there will be a project review.
Project management. I'm going to go through 3 sections today. These will include project initiation, project management, and monitoring and controlling. So, project initiation. Firstly, a location for the treatment plant had to be decided upon. 3 possible locations were looked at, as can be seen from the site map. After going through the regulations to do with the treatment plant, it was decided upon that the only suitable location was location 1, south of the engineering building. Here is a photographic image of where the treatment plant will be located. It will be sunk into the grass as to try to minimise aesthetic disruption to the area. The SPR treatment process consists of 5 main stages: fill, aerate, settle, decant, and idle. It's a form of activated sludge treatment in which aeration, settlement, and decanting occurs in a single tank. Wastewater gets pumped into the SPR during the fill stage. Its contents are then aerated and mixed prior to the settlement phase. The decant stage then occurs, followed by the idle rest phase. The cycle gets repeated a few times a day, while any excess sludge gets removed from the system during the rest phase. The sludge is then finally stored prior to removal off-site. Project management. There are 7 main PMBOK project management processes. These are scope management, time management, cost management, quality management, human resource management, communication management, risk management. For all these, documents were completed and were uploaded onto our website at wordpress.com. These will be discussed at a later stage in the presentation by Trevor. In relation to time management, a timeline for the project was drawn up. It shows the milestones for the project, such as when main sections start and finish. For example, as can be seen, project management execution started on the 2nd of January 2013 and was completed on the 12th of September 2014. Also, monitoring and controlling started on the 19th of May 2014 and was completed on the 28th of August 2014. With regards to cost management, a budget for all the main sections was set out. As can be seen from the table, the project management and consultancy cost €109,305. Site preparation and setup cost €7,790. The SVR tank construction cost €61,600. Construction of the sewer network cost €120,845. Reinstatement cost €54,695. Finally, there is a contingency fund of €100,000 added on. The total budget amounted to €454,235. Monitoring and controlling. An earned value management plan (EVM) was used for the project. This technique used to show a project schedule status and cost status. It defines what's been spent and value earned in terms of completed work. It's an effective monitoring tool. From the EVM, it can be seen that the project was ahead of schedule and under budget. A document showing the earned value management can be viewed on the website, showing the breakdown costs for the construction stage in great detail. Next up is the project design.
The first element of the project to be brought forward for design was the SBR treatment unit. In order to effectively design the treatment unit and the following elements, a site survey was completed. The site survey consisted of taking spot levels, curb lines, manholes, road centre lines, existing structures and obstacles around campus. Using the information obtained during the site survey, a survey drone of the campus was prepared as shown below. This survey drone was used extensively during the design process for both hydraulic and system designs. Following the site survey, a system design was completed for the SBR unit. The SBR was designed to treat 30 metres cubed of daily influent from the engineering building at AIT. The system was designed to incorporate a 60 metre cubed equalisation tank, which will provide over and above 24-hour storage in the event of breakdown or maintenance requirement. The SBR was designed with 12.5 metre cubed aeration basin. The SBR was designed to treat 7.5 metres cubed of influent in each batch. The deficit will allow for a freeboard in the tank and also for sludge storage. The plant will operate on a 6-hour cycle, which will be detailed further in the following section. The plant will utilise fine bubble membrane diffusers to maximise efficiency during treatment. Also, a post basin equalisation tank will be provided with a similar size to that of the aeration basin. This tank will provide post-treatment storage and allow for more efficient pumping of the effluent to the municipal sewer. The post-basin equalisation tank has been designed similarly to the aeration basin, with fine bubble membrane diffusers provided. This will allow the post-basin equalisation tank to act as a standby reactor in the case of a breakdown. P&ID diagram below demonstrates the treatment process. Influent will be pumped from the engineering building to the treatment works. Before entering the treatment system, the influent will be screened. Following screening, the influent will pass to the equalisation tank, where it will be stored until there is a sufficient volume to fill the SBR reactor. It will then be pumped to the SBR reactor, where it will be treated. Following treatment, the effluent will be pumped to the post-basin equalisation tank and subsequently released to the municipal sewer. Settled solids from each of the 3 tanks will be removed by submersible pumps and stored in a sludge storage tank for subsequent removal. The animation below depicts a typical treatment cycle. Influent enters the SBR equalisation tank. When a sufficient volume is contained in the equalisation tank, it will then be pumped into the reactor. When the reactor is full, the effluent will then be aerated. Following aeration, the mixed liquid will be allowed to settle. This will allow the formation of a clear layer of treated effluent at the surface. Throughout the settling stage, this layer of clear liquid will increase in depth. When the settling stage is complete, this clear liquid will then be pumped into the post-treatment equalisation tank. The treated effluent will then be discharged to municipal sewer and the treatment cycle will repeat itself. The structural design of the SBR unit was also completed. Firstly, the SBR treatment unit was checked in accordance with Eurocode 7 for uplift. The unit was designed as a reinforced concrete tank, incorporating longitudinal and transverse reinforcement. The reinforced concrete tank was checked for shear, crack widths and deflection in accordance with Eurocode 2. Following completion of the design, reinforcing drawings and bar schedules were prepared for the tank. Also, general arrangement construction drawings were prepared. In addition to the design of the SBR treatment unit, a hydraulic design was also completed for the sewer system.
The hydraulic design of this project is in 2 parts. First of all, the sewer network layout and the sewer design. This is the layout of the proposed sewer for the engineering building. The route was selected to minimise impact on the institute. The first manhole is the discharge collection point of the sewers from the engineering building, shown on the left-hand bottom side of the picture. It flows by gravity and is pumped up the hill and flows to the SBR. As can be seen, the route follows the estate road and connects with the local authority sewer on the west side of the college. For a more in-depth knowledge, we will go to the next slide. The design criteria for this facility is based on using BS 8301 1985 Section 3. The maximum peak discharge was calculated to be 13.2 litres a second. that is, all appliances in the engineering building being used simultaneous, however, under normal working conditions, with a maximum number of persons at 500 at a daily water usage of 60 litres a person per day for a 9-hour day and a dry weather flow of 3, the average discharge is 2.78 litres a second. For calculation purposes, WAVN pipes are used, which have inside diameters of 151.6mm and 237mm. These pipes are 160 and 250mm outside diameters, respectively. The Colebrook-White equations are used for the calculations. Using a 160mm pipe from F1 to F3, the pipe is proposed to be at a gradient of 1:22 to get a self-cleaning velocity greater than 0.7 meters per second, as per BS 752/4, but also allowing for the maximum peak discharge of 13.2 litres a second, so a velocity of 0.74 meters per second is achieved. The sewerage is lifted 6.4 meters by pump from F3 to F4 at a flow rate of 15 litres a second, where from F4 to F5 gravity brings it to the SBR. When treated, the water and dissolved solids are released at a rate of 15 litres a second from the SBR from F6 to F7, which is a backdrop manhole. Continues by gravity using a 160mm pipe. The pipe changes to a 250mm from here on. The sections between F7 and F14 is divided into 6 segments of straight pipework with 9 manholes in between. At F14, the treated effluent is lifted approximately 4.7 meters by pump, where it flows by gravity by pipe to connect to the local authority foul sewer system in the public road at F15. There are 2 pumping stations, F13 and F14. The difference in elevation between the 2 points are 6.4 meters and 4.7 meters respectively. The pumping station and sewer were designed in accordance with BS EN 752. The maximum flow rate for an hour is 47.52 meters cubed. Using the pump calculation sheets in Appendix 2 of the hydraulic design, it was decided to get 3 goals pumps, submersible sewage pumps, 2 for constant use and 1 as a spare, or similar make with the same performance either. These pumps can discharge 120 meters cubed at a head of 8 meters. These are supplied by www.shopspumps online at €1,673 each. Each pump has a 100mm rising main as required by the EPA treatment systems for small communities, business, leisure centres and hotels. The spare pump could be on standby at F3 when not required at F14, because this is the main catchment point from the sewer of the engineering building. Flow rate can't be controlled here, whereas at point F14 the flow rate can be controlled from the release mechanism on the SBR. These pumps are designed for the maximum flow rate, but the most likely flow rate is 10 meters cubed per hour. A backup generator should be provided in case of power outages. This picture shows a longitudinal section through the hill from F3 to F5. All longitudinal sections are available on wordpress.com, which will be discussed later. The next slide is the construction phase.
For the construction phase of the project, we'll look at 3 main areas: construction scope, construction schedule, site setup, excavation and construction. Construction scope. The requirements for the construction stage are identified. The next up is to define the scope. This is done by a document which is called the scope statement. The scope statement outlines the results that the project will produce and the terms and conditions under which TNLS contractors will perform their work. Following this will be the work breakdown structure. This involves subdividing the project deliverables and breaking them up into smaller, more detailed components. Following the completion of the work breakdown structure, a work breakdown structure dictionary is completed. This defines each component. Next up is the construction schedule. The construction time frame was completed. This image shows the different milestones for the construction stages. The contractor will start on site the 19th of the 5th, 2014 and will complete the works in the 28th of the 8th, 2014. Next up is the site setup. Once the completion of the schedule, you'll see here the engineering building to your left hand side and the urban buildings. The SPR will be positioned on the hill west of the engineering building. Following this will be the site setup, where the contractor will erect his site fencing. He will then install his offices and containers for storage. Following this will be the arrival of the plant and machinery to carry out the works. The existing car park will be used for the compound, where this will reduce the cost of drawing in and out of materials. Following this is the access route. This involves the stripping and storage of topsoil on the site. We will use a 13.5 ton excavator and a 6 ton dumper to remove this topsoil. Following that will be the placing of 75mm hardcore. This will be placed on the access route. Following that will be the use of a vibration roller to compact the material. Following the completion of the access route, the excavation for the SPR will commence. We'll use a 22.5 ton excavator to excavate the hole. We'll also need 2 HGVs to remove the material off site. Also, a small quantity of material will be left on site for the backfilling process. Also, safety gates will be positioned around the tank during and after the excavation. Following that will be the setup of a traffic management plan for the sewer line construction. This will involve erecting signs and traffic lights, exiting and entering the area under construction. Following the traffic management plan will be the excavation of the trench. As shown, safety barriers will be located around the trench at all times. Due to the deep excavations in the area, trench boxes will be used. Placing of a 2 to 5 pipe in the trench. As you can see, the completed SPR unit in the hill location west of the engineering building, surrounding it with security fencing and an access gate, and also an access route to the plant.
Throughout the foregoing phases, a project-specific WordPress website was maintained. The website primarily acted as a project management plan, but also was utilised to record information in relation to monitoring, controlling, design and construction. The website is freely available at wordpress.com for all parties related to the project. As previously stated, the website primarily acts as a project management plan. As such, all information in relation to project initiation and project management plan are available on the website. Each activity is broken down with discussions and relevant documentation supplied on the webpage. All documents are freely available to view on the website. In addition to acting as a project management plan, information is also available for monitoring and controlling of the project, design, construction and miscellaneous, including meeting minutes. To review, TNLS were appointed consultant engineers and project managers for the construction of a wastewater treatment plant at AIT for the treatment of wastewater produced by the campus's engineering building. Project management planning for the project was completed by TNLS in accordance with guidelines set out by the project management body of knowledge. TNLS also completed numerous designs for the project, including hydraulic, structural and system designs of the SPR. Also, comprehensive planning of the construction stage of the project was also completed. A WordPress website was also utilised to form a project management plan and also to store all relevant information in relation to the project. Thank you for listening. If you require any further information, please do not hesitate to contact any member of the project team, details given previously. Also, you may contact us through our WordPress website.